Welcome to The Explainer. Ever stop to think about how, when an orthodontist moves one of your teeth, they keep all the others from getting dragged along for the ride? Well, today we're digging into the hidden physics and some really clever engineering that makes a perfect smile even possible.
All right, so let's just jump right in with this question. It seems simple, right? But the answer really gets to the core of how all of orthodontics actually works. Because if you push on one thing, well, something else has to push back.
And that whole pushback thing, it's all about basic physics. We're talking about Isaac Newton's third law of motion. You know the one, for every action, there's an equal and opposite reaction. And yeah, that law doesn't just apply to rockets and planets, it's happening right inside your mouth.
So to manage this, orthodontists use a concept they call anchorage. And honestly, the name is perfect. It's just like a ship's anchor. You drop it to hold the ship steady. In orthodontics, the anchor unit is a tooth or a group of teeth that are supposed to hold steady while other teeth get pulled or pushed into their new positions. But here's the catch, and it's a big one. The very same force that you're using to straighten a crooked tooth is also pulling back on your anchor teeth, trying to move them out of place. It's this constant, invisible tug of war, and if you're not careful, your anchor is going to start to drift.
Now, you'd probably think that the main thing an orthodontist has to fight against is just simple friction, right? You know, the resistance of sliding a bracket along a wire, kind of like dragging a heavy box across the floor. But the real story is way more interesting, and the true villain here is something else entirely. So, check this out. On one hand, you have friction, which is just what you'd expect, surfaces rubbing together. But then there's this other force called binding, and it is so much stronger. Binding is what happens when the bracket on the tooth tips just a tiny bit and its corners literally dig into the arch wire. The analogy here is perfect. Friction is just dragging the box, but binding is that box getting totally jammed sideways in a doorway. Much harder to move.
And this process happens almost instantly. The force pulls on the top of the tooth, the crown, but the root down in the bone resists. So what happens? The tooth naturally starts to tip. And it only takes a minuscule amount of tipping for the sharp corners of that bracket to engage the wire, creating that powerful wedging effect we call binding.
And this number just brilliantly illustrates how dominant binding is. Once a tooth tips by just 7 degrees, which is almost nothing, friction becomes basically insignificant. Over 90% of the force needed to move that tooth is now being spent just overcoming this powerful binding effect. It's crazy.
Okay, so we get it. Binding is a huge deal. But understanding these forces is one thing. Actually controlling them is the real art. And orthodontists have developed a whole playbook of clever strategies to manage this anchorage problem and win that tug of war.
Here are 3 of the classic, low-tech but super effective methods. You can reinforce your anchor by simply adding more teeth to it. You can subdivide the movement, which means moving teeth one by one. Or you can do this little 2-step where you intentionally tip teeth first and then straighten them up later.
Reinforcement is really just a numbers game. This quote from the research explains it perfectly. It talks about PDL area. That's the periodontal ligament, the tissue that holds the tooth in its socket. Think of its area like the tooth's footprint in the jaw. So, to make your anchor strong enough, the total footprint of your anchor teeth has to be at least double that of the teeth you're moving. And get this. If you're sliding teeth and dealing with all that binding, you need that ratio to be a massive 4-to-1.
And the subdivision strategy follows that same logic. Instead of trying to pull, say, all 4 of your front teeth back at once, an orthodontist might just pull one canine back first. This way, you're pitting the resistance of a single tooth against a massive anchor unit made of multiple molars. The downside? Well, it makes the whole treatment take longer because you're moving teeth in different stages. But see, all of these traditional methods work by balancing forces between teeth. What if you could create an anchor that was completely 100% immovable? Well, that's where a true revolution in modern orthodontics comes into play.
Meet skeletal anchorage, or what are more commonly called TADs, temporary anchorage devices. These are tiny, specially designed screws that an orthodontist can place directly into the jawbone. They act as a fixed, totally stable point that simply will not move. This changes the entire equation.
And they can be used in 2 main ways. With direct anchorage, you attach a spring or an elastic right from the screw to the tooth you want to move. Or with indirect anchorage, you can use the screw to just lock an anchor tooth in place, basically turning a regular molar into a super anchor that absolutely cannot drift forward.
This is the ultimate solution to the anchorage problem.
Why? Because that whole equal and opposite reaction force from moving a tooth isn't applied to other teeth anymore. It's applied to the jawbone itself, which is, for all intents and purposes, an immovable object. You're not sidestepping Newton's law. The force is still there, but you're directing it into the bone, completely protecting the other teeth.
So the crucial point to take away here is that this technology just opens up a whole new world of possibilities. Tooth movements that were once considered impossible or would have required complex surgery are now achievable. And it leaves us with a really fascinating question. With the ability to anchor directly to bone, what are the future limits of moving teeth? What's next?